Hello everyone, welcome to our next lesson. We're going to begin Unit 5 in this lesson called the derivative, and this is where we get into an introduction to a large branch of mathematics referred to as calculus. What we're going to be doing in this video, we're going to start limits. I'm going to look at something called continuity and also graphical limits. How do we determine from a graph what the limit is of a function as x approaches a certain number? Okay, so let's get started. What do we mean by continuity of a function? Well, basically a function is continuous if there are no breaks or gaps or holes in the graph. It's like you can take your pencil and just draw a nice smooth continuous curve. This graph that's shown here is a continuous function because I can lay my pencil down and just begin to draw a nice smooth curve. I don't need to lift my pencil off the paper whatsoever, and I can continue in a nice fluid motion. That's what we mean by a continuous function. Here is an algebraic definition of what we mean by a continuous function, although you won't be tested on this. This goes a little more in depth than what you really need for this course. All you need to remember is a continuous function doesn't have any breaks or gaps in that. Here are different kinds of discontinuities that you could have in a function. These graphs are discontinuous. If you look at them carefully, you can see that there are breaks or holes. There are places where you would not be able to just make a nice continuous curve with your pencil. Let's have a look at what types of discontinuities exist in a graph. The first type right here, this is called an infinite discontinuity. And in general, what happens there is that your curve, your function, either goes to infinity or to negative infinity, and you have basically a hole somewhere in your graph. There's a place where the value of x is undefined. An infinite discontinuity traditionally, usually, occurs with a type of rational function. Remember that in a rational function, like any fraction, you're not allowed to have 0 in your denominator. In this case right here, if you look at y equals 1 over x, you can clearly see that your domain does not include 0. Because if you put in 0 for x there, you of course have 0 in your denominator. And that would traditionally result in an infinite discontinuity. The next type of discontinuous graph is called a jump discontinuity. And traditionally, you get a jump discontinuity when you have piecewise functions. Now, not all piecewise functions result in a discontinuity, but in general, most of the time they do. And you can see there's a gap here between the left-hand side and the right-hand side of your function. So that's called a jump discontinuity. And finally, there's another kind of a discontinuity. We're going to be looking at this one a little further, a little more, in more detail a little bit later. This is called a removable discontinuity. And what it looks like basically is like there's a hole in your graph. Now it's a very small hole, by the way. If you were to type into, say, a graphing calculator or even most graphing software, any type of a function that has a removable discontinuity, that hole is so small that you probably would not see it. Now, where do you get removable discontinuities? Well, again, we have a rational function right there. And you can clearly see, if you look at the denominator, what value of x is not allowed to be. What value of x must be excluded from the domain. Well, here you can see that x is not allowed to equal 3, is it? Because at 3, your denominator becomes 0. 3 subtract 3 becomes 0. That hole in your graph right there, I'll guarantee you one thing. That x value right down there, that x value is 3. And that's why there's a hole there. But why is it called a removable discontinuity? Well, because if you look at your numerator, you will also see that it also has a factor of x minus 3. So technically, because they're factored, those x minus 3's can cancel. right? Resulting in a function of just y equals x over 2, which is really the same thing as y equals 1/2 x. And that's a linear function. All right, that's a linear function with a slope of 1/2. And it would look something like the one there, not quite, but it would look something like that graph right there. So it's removable, meaning that if you cancel it, you basically end up with y equals 1/2 x in this case right here. But that doesn't mean, even if you cancel the terms, the whole does not vanish. It stays there, all right? So it's a discontinuous graph, even though those terms would cancel out. So that's the three types of discontinuities that you can have, that you're going to see anyway in this course. On the next page, now all they're asking you to do here is sketch the following graphs, state any types of discontinuity, and any values that are not in the domain. Well, you can just go on to desmos.com if you like and try these. This first one right here, this first function, you can see it's a rational function, and you can clearly see that x is not allowed to equal 2. 2 must be excluded from your domain. Notice it's not removable though. There is no x subtract 2 factor in the numerator, so it doesn't cancel. This is not going to be a hole in your graph. In fact, this is going to result in an infinite discontinuity. And what's going to happen is there's going to be a vertical asymptote right about here at x equals 2. And you can check this out on Desmos if you like. At 2, right there, you're going to have a vertical asymptote, and your graphs, one part is going to look something like this, and the other part is going to look something like this. Now, you can verify that by checking into Desmos if you like. But this is going to result in an infinite discontinuity. And you notice that from the left-hand side, if you look at this curve here from the left, what happens is the function begins to approach negative infinity. All right, what y value is it getting closer and closer to? Well, that's kind of going down toward negative infinity. But your graph on the right-hand side, as it gets closer to 2, and that's what we mean by a limit, by the way, when we start looking at limits now in just a moment. What's the limit as x approaches 2? From one side, it goes to negative infinity, but from the other side, it actually approaches positive infinity. That's the y value that it's getting closer and closer to. In general, if you have rational functions, and if you have to exclude values from the domain because it would result in 0 in your denominator, and if it's not removable, then what's going to happen there is you're going to get this infinite discontinuity. The second one is also a rational function, isn't it? Right? And you can clearly see in the denominator that you're not allowed to have x equals 0. So 0 would have to be excluded from your domain right there. But in this case, it's removable because if you look carefully, you can see there's also a factor of x in your numerator. So they could, in fact, cancel like so. Now, that doesn't mean that suddenly you're allowed to use 0 for x, because no, you're not. In the original function, 0 had to be excluded from their domain. This one is going to result in a hole in the graph. All right? That's going to result in a hole in your graph. So that's what we call a removable discontinuity. And in fact, what it would look like, if you were to graph this, you would basically end up with a parabola like this. And here's where the hole would be, somewhere around there. And then it just continues in a parabola like that. But now if you were to graph that on your graphing calculator, you wouldn't see the hole. It's so small. It's so very, very, very tiny. And the third one they have there, now there is a piecewise function. All right? And piecewise functions usually, not always, but usually result in something called a jump discontinuity. And in fact, if you were to graph this one, if you were to graph x cubed for x less than 0, now notice less than, so there's a hole right there, a hollow dot, and there's your cubic function when x is less than 0. And the other part, negative x plus 2, that's just linear, but you have to graph that when x is greater than 0. So what you get there is there's a y-intercept of 2, all right, and the slope is -1, so it would look something like that right there. And that's a jump discontinuity. Oops, that's supposed to be a u there. So those, again, are the three types. And again, you could just go onto Desmos and type those in and get a little more detail on what the graphs look like. Don't be surprised, though, if you don't see the hole for a removable discontinuity, because it's so very, very, very tiny, you see? Very small. There's only one value of x that you're not allowed to put into that function, and that's 0. But anything else you can put in, so anything incredibly close to 0, and that's why you don't see the hole on your calculator. Okay, what about limits? Graphical limits. We just said that really when they're asking for the limit of a function as x approaches a certain value, you have to consider approaching that value from the left and also from the right. Okay, and we're going to look at some of the notation for that here. Now, actually, they have it right there. Look, that's what they refer to the limits. Now, you'll notice that this function here, the one that they've drawn, looks like a nice parabola, doesn't it? All right. Well, they're using a value of 3. What would happen to this graph, to this curve, as x approaches 3 from the left and as x approaches 3 from the right? Now, it's a nice continuous curve to begin with, so these are probably some of the easier cases that you're going to see. Note the notation right here. Now, that's referring to x approaching 3 from the right-hand side. Okay? And this notation down below as x approaches 3 from the left-hand side. Now, that does not mean 3 is negative. 3 is positive in both cases. Numbers that are very, very, very slightly bigger than 3, you can think of numbers such as 3.1 or 3.01, 3.0001. You're just getting closer and closer and closer to 3 from the right-hand side. Now, here's 3 right there on your x-axis. So here's the point that they're referring to. Well, as we approach 3 from the right-hand side, that means that take your pencil or my pen or whatever, and I'm going to go closer and closer and closer and closer and closer and closer to x equals 3. I'm going to get incredibly close. Now, what y value is my pencil getting closer and closer and closer to? Well, if you look carefully, it appears that C is getting closer to that point anyway. That would refer to a y value of 2, wouldn't it? So the way we write that is the limit as x approaches 3 from the right-hand side. Notice a little plus sign there. That doesn't mean positive. It means from the right-hand side of f of x. And the y value that I'm getting closer and closer to is 2. And that's the way we write the limit. Now, for the same curve, for the same function, what's the limit as x approaches 3 from the right-hand side? Now, like I say, this is a continuous graph. This curve is continuous. You're definitely going to have the limit exist here because you're going to be approaching the same y value from left and right, no matter which x value you pick. Now, watch my pencil. I'm going to sort of take my marker and I'm going to go closer and closer and closer and closer and closer to 3. But I'm never going to get to 3. Remember, I don't put my pencil on 3. I just get closer and closer and closer to it from the left-hand side. Now, that would mean numbers such as 2.9, 2.99, 2.9999. Not 3, but you're getting closer and closer and closer to 3. Okay? And what y value am I getting closer to as well? Well, it's still 2, isn't it? Now, do you notice that from the left and from the right, they're both approaching the same y value? And because of that, in this case, we say that the limit actually does exist for this function. And in fact, the limit is equal to 2. And we would be able to write the limit as x approaches 3. Now, notice you don't have to say from the left or the right now because you know that the left and the right give you the same result. And there you go. You'll be able to write that the limit is actually equal to 3 in this case. This is also shown in a table of values like this. In fact, you can get the same result by looking at this table right here as we just got from the graph. And in fact, I've actually asked questions on quizzes and tests with tables just like this and asking the students, what's the limit as x approaches 3 from the left? Or what's the limit as x approaches 3 from the right? If you look at these x values right here, you can see that they're all less than 3, but they're getting closer and closer and closer to 3. This would in fact be the limit as x approaches 3 from the left-hand side. So put a little minus sign there. And you can see that these numbers here, they're getting closer and closer to 3. Well, what are these numbers getting closer to? What does it look like? 1.997, 1.99997. Oh, by golly, it looks to me like they're getting closer to 2. This table, notice that the x values, again, they're getting closer to 3, but they're all a little bigger than 3 this time, aren't they? So this is showing values of x approaching 3 from the right-hand side. But again, if you look at the y's, look at the y values. What are those y's? What does it look like it's getting closer and closer and closer to? Well, again, it's looking like it's getting closer to 2, doesn't it? All right. Remember that limits mean you're approaching a certain number from the left and from the right, but you never actually get to that number. In fact, that point may not even exist. That could be a removable discontinuity or some other type of discontinuity, but you can still have the limit from the left and the limit from the right. Okay, so you get closer to the number, but never equal the number. Okay, so that's what we mean here by the definition of a limit. Here's the notation right there. The limit as x approaches a of f of x equals L. That's the way we would write it. And the limit actually exists if the limit from the left as x approaches a from the left equals a certain number, and if the limit from the right as x approaches a is equal to the same number. But those two limits, they have to be the same. And if they are the same, then we can say that the limit exists for that function. If they're different, sorry, the limit does not exist. So let's look at some examples here now on page 6 in your notes. So this is saying determine the left and right hand limits as x approaches 0. Okay, so they want us to approach 0 here. Now remember, a limit can approach any x value, any number whatsoever. They're just using 0 here. And they want us to use the graph, so that's why these are called graphical limits. And then secondly, after you've looked at the left and the right hand limits, determine if the limit exists. Okay, let's look at the first one. What do we have? Okay, well, here's your x value of 0 right there. You can see that. Okay, in fact, there's your x-axis right there, and there's your y-axis up above. Okay, so as x approaches 0 from the left, the way you would write that is the limit as x approaches 0 from the left-hand side of f of x. Now, I don't know what the function actually is, so I'll just call it f of x is equal to. Now, take your pencil or your pen, whatever you're using, put it on the curve to the left of that x equals 0, and I want you to start moving your pencil closer and closer and closer and closer to that x value of 0. Now, don't actually put it on 0, but just get closer and closer and closer to 0. What y value is my pencil approaching? What y value is it getting closer and closer to? Well, if you look carefully, that y value right there is 1, isn't it? So the limit as x approaches 0 from the left of f of x is equal to 1. Now let's try it from the right-hand side. And I'm pretty sure you're going to get the same limit, because this is a continuous curve. If they're continuous, they're going to be equal anyway. So let's see, what's the limit as x approaches 0 from the right-hand side of f of x? So let me put my pencil here. I'm getting closer and closer and closer and closer to x equals 0 from the right. So all these values, now these x values are bigger than 0. Now don't actually put your pencil on 0, but again, what y value is my pencil approaching? Well, again, it's approaching a y value of 1. And now if you look carefully, you can see that the limit from the left is equal to 1. the limit from the right is also equal to 1. And because those are exactly the same, we therefore say the limit exists for the function. Now remember, I never did put my pencil on 0. If there was a hole there in my graph, it doesn't matter. The limit would still exist because the limit from the left and the limit from the right are equal. So because of those two things, now we can write the limit as x approaches 0 of f of x. It's not necessary here now to say from the left or from the right because it's the same, really, isn't it? Is equal to 1. There's my conclusion. This limit does exist as x approaches 0, and the limit is actually equal to 1. So let's try that now with some of these other graphs that are here. Okay, let's try it for the second one. Right there. Here's my 0 again. There's x equals 0. The blue piece of the curve is to the left of 0, and this orange piece of the curve, actually they're lines, to the right. Well, that's bigger than 0. So let me see. What's the limit as x approaches 0 from the left-hand side? So that would be the blue line of f of x. All right. So I'll take my pencil, I'll put it right on that blue line, and I'll get closer and closer and closer and closer to x equals 0. But I'll never actually go to 0. Now, you see that? What y value am I getting closer and closer and closer to? Well, as x approaches 0 from the left, the function approaches 3. The y value looks like it's 3, doesn't it? That's the y value I'm getting closer to. Now, let's also do the limit as x approaches 0 from the right-hand side of the function. And again, I can just take my pencil and put it on the orange piece of the curve now and start approaching 0. So I'm getting closer and closer and closer, closer, closer. I can get as close as I want to 0 from the right. What y value is my pencil approaching? Well, this time it looks to me like the y value it's approaching is equal to 1. And by golly, look at that. That's a jump discontinuity, isn't it? But the fact of the matter is, the limit from the left is not equal to the limit from the right. And therefore, we can say the limit as x approaches 0 of f of x does not exist. All right, because it's not the same from the left and from the right. That would be your conclusion here. That would be your conclusion. So it's not a difficult topic. You're given a graph, and you basically just, as you approach a certain x value from the left and the right, what y value are we getting closer to from both directions? And if they're the same, then the limit does exist. Here's the third one, right there. Now look at that. I don't know if you can see it or not, but there's a little tiny hole in the graph right at the y-intercept. You see that? There's a hole there. Well, let's check and see what's the limit from the left and what's the limit from the right. And so let me see. So the limit as x approaches 0 from the left-hand side, that's a 0, of f of x. And again, I'll just take my pencil. Here's my 0. My x value is 0, so I'll approach it from the left-hand side. And as I get closer and closer and closer and closer, all right, to x equals 0, it looks like my pencil or the function is getting closer to a y value of 1. And if I try the same thing from the right-hand side, the limit as x approaches 0 from the right of f of x. All right, so I'll take my pencil and put it on that line again. And now I'm approaching 0 from the right-hand side. Now remember, you don't put it on 0, but you approach 0. And what y value is my pencil getting closer and closer to? Well, that one is also a 1, isn't it? Now, even though there's a hole there in the graph, the limit from the left is equal to the limit from the right. There's a discontinuity there. But for limits, that doesn't matter. So we can say that the limit does exist, even though there's a hole there, of f of x is equal to 1. That would be our conclusion for this problem. Okay? And I think they have one more there. And this is an interesting one because This is actually what we called an infinite discontinuity back just a moment ago. All right, so again, you can see here's 0. That's actually, remember back in unit number 3, that's actually one of those simple hyperbolas, isn't it? We did those. Anyway, let's find out about the limit. What's the limit as x approaches 0 from the left-hand side? All right, so let me see. Here's the left-hand side over there. So I'll put my pencil on the curve. It's very close to the x-axis over here. The x-axis is actually an asymptote, and the y-axis is an asymptote here as well. So let me approach 0. Now as I approach 0, what happens is the curve starts to swing down, 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 and it's getting closer and closer to the y-axis, but it's never actually touching, and it goes down, 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 forever and ever and ever and ever and ever. So what y value is my curve getting closer and closer to? Well, it's actually flying up to negative infinity, right? Those y values are just getting smaller and smaller and smaller. The limit as x approaches 0 from the right-hand side of f of x, so that would be this piece of my curve, and actually that starts out over here somewhere, again very close to the x-axis, because the x-axis again is an asymptote. And as I get closer and closer to 0, now the curve begins to swing upward. See that? And it goes up, 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 forever and ever and ever and ever. But now the y values are getting bigger, not smaller. So in this case, the limit is positive infinity. And you may ask yourself, is the limit from the left and the limit from the right, are they approaching the same number? Nope. They are not. So for this case right here, we would say that the limit as x approaches 0 of f of x, because they're not going toward the same number, does not exist. All right, and that would be our conclusion right there. Now, by the way, if they were both approaching infinity, if they were both approaching positive infinity, then the limit would exist. And in fact, positive infinity would be your limit. Or if they were both approaching negative infinity, well, that's still the same place, isn't it, kind of? So what would happen there is the limit would exist and it would equal negative infinity. So anyway, that's it for graphical limits. It is not a very difficult topic. It's not hard at all. Make sure you look these examples over, and I'll stop this video here. And when we come back in our next video, I'm going to look at algebraic limits. All right, well, what do you do? How do you find the limit of a function? Not if you're given the graph, but if you're given the actual function itself. What do we do there? What's the techniques that we use? All right, so that's what we'll look at in our next video. So I'll end this video here. Bye-bye for now.